Using a standard 52 card deck, find the following probabilities and leave your answer in as a reduced fraction. If the card is randomly selected, what is the probability the card is a diamond? So let me see if I can go up. I think I have all the cards. Okay, there they go. Here's all the cards. So a deck is made of four different, well, there's 52 cards and there's four different suits. So there's one, you could kind of think about this ace as like a one, and then it goes all the way through 13, like wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So like, you know, you could think of the jack is like at 11, queen is 12, and king is 13. So like it goes basically 1 through 13 in each of these four, you know, suits. So there's 13 clubs, there's 13 spades here, and there's 13 hearts and 13 diamonds. So the probability that it's going to be a diamond is there's 13 different diamonds. So it's 13, there's 13 cards in a 52 deck that are diamonds. So that our probability is 13 out of 52. Because there's 52 total cards that we could have chosen, and there's 13 diamonds that would make us happy and make us get the diamond, the card that we want, the diamond that we want. Okay, so that's and they they do want us to leave our answer as a reduced fraction here. So that means that we have to divide the top and bottom of the fraction. If there is a number that divides into top and bottom, that means with no remainder. We need to divide by that number, both on the top and bottom. So it's kind of hard to see if fractions can be reduced. That's a hard thing to, but here's my trick. Take the smaller number, whether it's the numerator or denominator, doesn't matter. Take the smaller number and prime factor that number. Prime factor means to find two numbers that multiply to be 13. So like, you know, here it's just 1 and 13, but you would keep, you know, breaking down by factoring each number until you get nothing but prime numbers. And so 13, actually the only way I could write 13 as two numbers being multiplied to be 13 is 1 and 13. So that there's no other way. I can't say like 2 times something equals 13. No. So that means that 13 is prime, because the only way that I can write it and factor it and find two numbers that multiply to be 13 is 1 and 13 itself. So any number that the only way you can factor it is by 1 itself means it's a prime. That means it's a prime number. So 13 is prime. So the only thing that I have to check is, does 13 go into 52? Because the only numbers that are going to divide into the numerator are the 13. So if there is a number that divides into the numerator and denominator, it must at first just divide into the numerator. And if there is a number that divides in the numerator, then 13 is really the only number other than 1, which doesn't count, then this is going to be completely reduced. If we check 13 doesn't go into the denominator, then we would say it's completely reduced. So let's see, does 13 go into the denominator? So I have to do 52 divided by 13 just to see if it goes in equally. Okay, 52 divided by 13, and it actually goes in 4 times equally. So we would divide the numerator and denominator by 13. And we get our final answer of 1/4. And there we go, that's for part A. Okay, if 2 cards are randomly selected, what is the probability of it drawing a king first, followed by drawing a 2? Okay, quickly, this is an and type problem, because the probability of drawing a king followed by drawing a 2. The probability of drawing a king and next drawing a 2. And whenever we calculate this and probability, we have to ask, are they independent? And I would say the are they independent? It means the probability of us drawing a king first, if we did draw a king first, does it affect the probability of us drawing a two? And it does. So we do need to, and I'm thinking we're taking the cards out. They're not really clear on this problem about whether they're taking the cards out. Is it with replacement or without replacement? So like I'm gonna assume that we're not replacing the card. If that is the case, then we're just going to do the probability of drawing king, because the probability and formula says multiply the probabilities. Times by the probability of drawing a two given that we drew the first card was a king and we took it out. Not replaced. So the probability of drawing a king, if we go back up here to see the full deck, there are 4 kings in a total deck of 52. So the probability of drawing king is 4 in 52. So I'll write this above here. 4 out of 52 is the probability of drawing a king. Now, if we did draw a king, then drawing a 2, I took out a king, not a 2. So there's still 4 2s left in the deck, but there's 51 cards total because there's a king missing. So this should be our answer. We should multiply 4 over 52 times 4 over 51. So that's 16 over, and then I do 52 times 1. 2652. That was 52 times 51, 2652. Okay, and then I'm going to do 16, the numerator, divided by 2652, and I get this 0.00603. And they said leave it as a reduced fraction. Okay, let's redo this again. So the thing with this problem is I need to make sure that that is completely reduced. And that's hard because it's a really big number. So the thing here is I want to quickly find, do they have a common number that divides into the top and bottom here? So I take the smaller number, that is the 16, and I factor 16. So it's 4 times 4, and then 2 times 2. So the prime factorization of the 16, if we is 2 times 2 times 2 times 2. But that's giving us a hint that the only really number that I have to check here that makes sure that this number does not go into both the numerator and denominator is 2. If 2 goes, because the 2s are the only prime factors of 16. So if 2 does not go into the bottom, then we're done. But I can already tell it does. So we're going to divide, because it ends in a 2 here. So I know that since any number that ends in an even number or 0, it's divisible by 2. So I know it's divisible by 2, but so we'll divide out. 16 divided by 2 is 8. Of course, I didn't have to do that one. And then 2652 divided by 2 is 13,026. Okay, but they're both still divisible by 2. So we'll divide by 2 again. And I get 4 over 663. So now the only number that go into 4, my prime factor 4, the prime factors are 2. So I know that the denominator, all I have to check is does 2 go into the denominator? And it doesn't, because it ends in an odd number. So the last digit here is an odd number 3. So I know that a number that's divisible by 2 will end in an even number, 2, 4, 6, 8, or 0. So I know that 2 does not go into 663 equally. So, and the only number that will go into the numerator is 2, well, technically, and 4. But if a number is not divisible by 2, then it's definitely not divisible by 4, because 4 has just twice as many 2's. So it's our answer that we want here is 4 out of 663. Okay, the next one, if 2 cards are randomly selected, what is the probability of drawing a heart first, followed by drawing the queen? Now, this is the and equation again, because they're asking the probability of getting a heart, right? The first event is a heart, and the second event is a queen. So this is an and type of problem. So we're probably, and again, I think we're going to do this problem. We're going to do this problem where we do not replace the card when we take out that first card. So we have to think about this one. Okay. This one's a little strange because the 2 events that they're asking us about, are not mutually exclusive. You could be a heart and a queen at the same time. Normally, we wouldn't worry about that only with the or problem or equation. However, that may play into how many cards we have left when we're doing this calculation. So we're going to do the probability of drawing a heart times by the probability that we're going to draw a queen, given that you drew a heart. The first card, you drew a heart in the first card. But because you could have drawn when you drew that first card, it could have been that you drew a queen that was a heart. And that would change the way we calculate this. So really, when we look at this problem, it's better to look at it to find the probability of 2 different events and think of it as different. Okay, we're going to find the probability that we draw a non-queen heart. Okay. And because either one of these would have made us happy, right? Um, I'll erase this. Okay. There are two events here are going to make us happy, and that is if I draw a heart other than a queen, and then draw a queen. That is going to make us happy, right? Okay, so we want the probability of drawing a heart, not a queen, then drawing a queen. Because this is one of the things that would make us happy, is if we drew some kind of heart and then drew a queen. Or we would also be happy with drawing a queen heart then drawing a queen. So we are happy with either of those happening. So we need to find the probability that either this happens or that happens, which would mean that, and those, the first card can't be both a queen or not a queen. So those are mutually exclusive. And so to find those, all I have to do is add the probability of drawing the first heart and not a queen, then drawing a queen, plus the probability of drawing a queen heart, then drawing a queen. So if we add those two probabilities together, then we'll find our final answer. So I'm just gonna put plus so let's look at the situation of drawing a heart, not a queen. What is the probability of that? Well, there's 13 hearts, so there's 12 that are hearts that are not queens out of 52. Then drawing a second card that's a queen, well, there'd be 4 queens left because the first one wasn't a queen out of 51 cards left. Then we would find what is the probability of that first one being a queen heart, which is 1 out of 52. That's only one heart. There's only one queen that is a heart. So there's 1 out of 52 for that one. And then the probability that the second one is a queen. Now, if we drew the first queen heart, there's only 3 queens left out of 51 cards. So that is the probability. This is the probability that we will draw the queen heart, then followed by another queen. This is the probability that we're going to draw a non-queen heart, followed by a queen. And now we need to, both of those would make us happy. So we need to calculate this probability of both and then add them together. So this one's 12 times 4, 48, over 52 times 51. So before you start some of these problems, you have to kind of ask yourself, could the event they're asking be satisfied in more than one way? And that's 3 over 262,652. And then I add those together, that's 51 over 2,652. And then now I have to, this is a really big number. And so it's hard to simplify this number. The easiest and fastest way for me is to find the smaller number 51 and to prime factor it. It's not divisible, and I can't even think about any two numbers that really multiply to be 51 to begin with, but we do have to check. I do notice that 5 plus 1, if you add the digits, you get 6, which is divisible by 3. So I think 3 times something will be 51. So let's look. And that's 17. So 3 times 17 is 51. 17, I can't break 17 down or factor 17 down even further by saying that, like, some number times some other number equals 17. So 17 is prime. So the only way that I can reduce, the only numbers that divide into 51 are, or only numbers I have to check that divide into 51 are 3 and 17. No. Well, the only numbers that I know divide into 51 are 3 and 17 and multiples of those, but 3 and 17. So the only numbers that I have to check to make sure that this is completely reduced, all I have to check is that 3 doesn't go in the denominator and 17 doesn't go in the denominator. And as soon as I know that 3 and 17 don't go into that denominator, then I can say this is completely reduced. So I say 20, I'm just going to do 2 calculations only. 2652 divided by 3. So that it does go, it is divided by 3. So if I divide by 3, then the top number is 17 and the bottom number is 884. Now 17, like I mentioned, is prime. The only number we'll divide into 17 is 17. Well, and 1, but 1 doesn't count. So the only number I have to check to make sure that this is completely reduced, I have to make sure that 17 doesn't go into 884. It does go 52 times. So I divide the top and bottom by 17. I get 1 over 52. And that is my answer for this second part here. All right, thanks for listening. Bye.